Okay, so this is the continuation of the lecture on Wednesday. Um, so activation records are an important implementation technique for implementing recursion, but it's also used for many other things. Um, so it's an important fundamental uh, uh, concept behind programming languages and how they're implemented. So as a program executes, methods call other methods. And as each method is called, the system creates an activation record. Um, yeah, this is an important concept. Activation records contain the parameter variables that are passed to the method on that particular call and local variables of the called method, uh, both of which are independent if you should have a recursion. So, for example, here's the public fact method that computes the factorial. It has a parameter n, it has a local variable ans, um, and both of those have to be unique for each activation. So, and remember in this factorial, we compute the factorial by multiplying the parameter n times the factorial of n minus 1. And then, of course, our base case is that n equals 1. Um, so here, invoking factorial of 3 will create an activation record in which the parameter n has the value 3, and at least at the beginning of execution, the answer has the value 1. Um, and of course, variables values can change during the execution, and that, of course, happens. So, yes, this is a good quiz question in order to address activation records. So how does that actually work? So each activation of a method creates an activation record. Um, and there is a section of memory reserved by the Java runtime environment. In this case, in other languages, it's their runtime support um, that will create, has a large chunk of memory called the stack, which is where all the activation records are put. So here we have our simple factorial again. Um, the activation record, in addition to local variables and parameters, contains a reference to the caller, space for local variables, and space for copies of parameters. So here we have our main program. is executing fact of 3. When we make this call, of course, v has no value yet, or it's initialized to some old value. Fact of 3 activation record, the parameter 3, it has its local variable, at least initially, has the answer 1. It then calls fact of 2, which creates its activation record, where in its activation record, the value of n is 2. At least initially, the answer is 1 also. These are different copies, of course. That's the whole idea of activation records. It's such a different copy for each activation. That, in turn, calls fact of 1, whose activation record has the value 1 for its local copy of the parameter n. Initially has the value of ans is also 1. When a method returns, the return value is passed back to the caller, and the reference to the caller means that the Java runtime support knows how to do that, or the code generated by Java, because it has a reference to the caller, and where the caller invoked the called program, then this return can occur correctly. And on the return, the activation record is deleted, and the caller's activation record is restored as the current one. And then when that return takes place, then this is deleted. This becomes the current one. When this return occurs, then this is deleted, and this becomes the current one. So each method call gets its own activation record containing parameters and local variables, and it helps to maintain the correct execution control flow. Statement execution flow of control we think of as while loops and if statements, but also method calls affect the control flow of the execution. And so that's what the activation records contribute there. When the method is called, the caller's execution is suspended. Control flow is passed to the calling method, caller method, called method, the called method. And the calling method is suspended. So the system needs a way of keeping track of all that, and the caller's current position of execution, the program counter, is saved in the activation record of the called method, so that the caller's execution position is saved in the called method. When the called method returns, this position is used to resume the execution of the calling method. And that's all taken care of without very much effort. So let's look at it again. Each activation record, each activation of a method creates an activation record. The activation record contains reference to the program counter of the caller at the point of call. It has information that allows the called method to return reasonably. And when that happens, the current activation record is deleted after the information about how to get to the caller is established. And then the caller's activation record is restored as the currently executing one. So again, with this fact execution, the only difference between this and the last one is that we're explicitly are showing the program counter. We don't know what there will be some program counter for the main program that will be the OS is called, or the Java runtime environment in our case. But once the main calls fact, the program counter for the main keeps track of that's where to start up again when we return. In the recursion, program counter for the recursion is line 4. So that is restored. That is contained in each of the recursive calls. And then they all return as specified by the program counter of the caller. So obviously when an activation record is removed, the caller's activation record has to be established. And you should remember a little bit about the stack data structure from 4.15, if you were in 4.15. It's a last in, first out, or LIFO. And so that's exactly what is happening when you're making these method calls. It is a stack. The top of the stack is the currently executing method. The next below that stack is the caller to that method, and then there's a caller to that method and caller to that method. So every time we have an activation of a new method, its activation record is pushed on the stack, and all the others are saved on it. So when it returns, we just have to pop the activation record off the stack, and that restores the calling method's activation record. So here's a new topic, tail recursion. It's useful to understand how recursion works in certain ways. We say that if there's no code to be executed in a function after the recursive call, we say it's tail recursive. So here we have a tail recursive print statement that is printing all the numbers from n down to 0. And well, it's printing the digits of a number. And the recursion, it prints out the the modulus of the number with a space. So this is going to actually print the digits in reverse order. And then it recurses on the div of that, so that this digit that just got printed here is not part of this division here, and then it recurses. Well, there's absolutely no code executed after this line, which then returns to the previous call, which returns the previous call, and none of them have to do anything after they've had their recursion. Now, we could just as easily, here's another variation of this, which prints the which does the recursion, and then at the end of the recursion it does the print, and then comes back up and prints, and comes back up and prints, and comes back up and prints. And so this is not tail recursive. Here the print statement is done after the recursion. What's the difference? Tail recursive function does nothing after the recursive call, which says that it does nothing on the way back up the recursion. A non-tail recursive function does something on the way back up. So remember, a stack reverses the order. Push 1, 2, 3, you get pop 3, 2, 1. A tail recursive function takes no advantage of the stack because there's nothing that needs to be done on the way back up. A non-tail recursive function does. There's some computation. It has to actually restore the activation record and do something with it. A tail recursive function, although the activation record is restored, there's nothing to be done except return to its caller. So what this means is that it's really easy to convert a tail recursive function to a non-recursive iterative version. And this might be desirable. Well, it's desirable at this point simply as a way of thinking about recursion and how it relates to iteration. But in terms of a compiler can actually generate code for a tail recursive function that is just as efficient as an iterative function, but has the elegance and the clean structure of a recursive function. So to convert a non-tail recursive function to a non-recursive function, in general, requires a stack. So is this tail recursive? Okay, this is a modulus function. And yeah, it's tail recursive because once we evaluate the mod recursion, there's absolutely nothing that gets done. So how do we convert? Let's convert the mod function to a non-recursive function. One or more method parameters may become local variables. The recursive call becomes a loop. So here's our tail recursive version. The value of v at each new recursion level is v minus d. And this is the key part of the loop body in a non-recursive version. So we take the if becomes a while with an inversion because this is the termination condition, this is a continuation condition, and then the parameter change that is the reduction of the parameter here just becomes the code that's executed in the loop. So recursion termination condition v less than d transforms to its complement in the continuation. Okay, is this tail recursive? Okay, here we have a string reverse. If the length is 0, we return it because it's an empty string. Otherwise, we take off the first character and we get the rest of that character, we reverse the rest of it, and we add on the first character at the end. Well, no, it's not tail recursive because we have this function that takes place after the recursion. It's all on the same line, but it's still, the recursion takes place and then something else has to happen in the code rather than simply returning. So how do we convert a non-tail recursive to recursive? Well, I mean, there's always a way. Certainly, you can simulate what the language does with an activation record. But sometimes you can take a non-tail recursive function and can change it slightly to make it tail recursive. Key thing is, rather than building the answer on the way back up, we want to build it on the way down. Is that possible? So sometimes that can be done by adding a new parameter to pass the partially calculated interim solution down the recursion. And then the final calculation is then returned from the bottom unchanged. That's what we did with the anagram, basically. And sometimes this requires a helper method to make it clean. So here's the reverse method that is not tail recursive. We don't want to change the public interface here because as a tool, for example, it should be nice and clean and not pass extra parameters that don't belong, that the user doesn't need to see. So what we usually do is we create a helper function, usually private, and here what we do is we add the extra parameter, which is the portion of the reverse string as we're going down the recursion. And so here we have word, the first parameter is still the piece of the word that hasn't been reversed yet, and the second parameter is the part that has. So as soon as word length gets to 0, we return not word now, but our word, which is the completely reversed string. Otherwise, we pass down the concatenate, we pass down the rest of the string as the first argument, which is pretty much what we did before. But we concatenate positions character 0 with the portion of the string that's come down reversed already. And so now all the concatenation work is done before the recursion. And so this is now a tail recursive method. Okay. So now that we have a tail recursive version of reverse, we can convert it to a non-recursive quite straightforwardly. We simply take the two functions here, two computational units here, which is part of the recursion, which is to take the substring of all but the first character, and then to do this concatenation, they become two separate statements in our while loop. And once again, the condition is reversed, and okay. Revisit iteration versus recursion. Any recursive solution can be done iteratively. Tail recursion occurs when the recursion occurs at the very end of the execution and no other execution takes place. Those are very easy to convert to a non-recursive, to an iterative solution, and many compilers will do that. If there are a few local variables, it's also very easy for a user to do it by hand. Other forms of recursion can also be done iteratively. And certainly any iterative solution can be done recursively, although it's probably not convenient. All we have to do is turn the for loop body into a recursive method with the loop index as a parameter, along with all the other parameters that that loop index might need. Generally, this is not desirable. You want to think of recursive solutions naturally, not as a method of implementing a naturally iterative solution. You can also have a while body for recursive method. The real decision about these is design and performance, and ease of coding. And in general, the ease of coding is the most important criterion and should be the one that dominates your decision. Testing, you have to be careful in either way. Recursive solutions are probably a little easier to get into loops, but if you're careful, that's not a big deal. Recursive solutions on the surface of it can be less efficient, but that isn't always the case. So ease of coding, that's the big deal. That's the one we really want to think about. Recursive factorial is very simple, but it's also simple iteratively. All right, so there's an iterative solution. Anagram. Recursive solution took a little thought, but it's pretty nice. Try to think of an iterative solution. Towers Hanoi, the recursive solution is pretty straightforward. I have trouble thinking of a iterative solution that isn't just driven by what I know the recursive solution does. Some people think that it's easier to debug iterative solutions. It's not with a little bit of thought, you know where the problem will be with a recursive solution. It's that base case, and usually it isn't that hard to get it right, or at least recognize pretty quickly that you didn't, because when it starts looping infinitely, it doesn't take long for you to figure out you didn't get your base case right. And a key thing in the algorithm is that the recursion step has to get closer to the base case every time. Performance. Creating activation records is expensive compared to doing a loop iteration. That could be a factor. Activation records do take up space, which you wouldn't need in an iterative solution as many. Memory itself is less of a problem in today's machines because of the large memory and virtual memory. So memory typically isn't as big a deal, but it could be. And the key is the recursion you choose to do really a significant impact on the application? If you're recursing a few times over huge amounts of data, it's just not going to matter. If you have huge amounts of data and you recurse on every single one, then it could matter. So look at the spiral app and tree app examples in the text. Recursion both is based on drawing lines such that the angle between successive pairs changes by a fixed amount and the length of each line is shorter than the last. The base case is a line that is 3 pixels long. Clearly, the recursion has to stop. It has to keep getting smaller. Tree app has 2 new recursive paths spawned at each step. The base case, therefore, must be reached along all paths. Okay, so next Wednesday, we're going to go to start data structures.